Our topic today is new technologies to propel renewable energy prospects. With us again, very friend of us, Cleveland M. Jones, Professor Cleveland Jones. You
Nice to
can
be with
see
you again, Cavagna. This is
it's
good.
always a pleasure, always a pleasure. Very good. Let me maybe we could say that some of the technologies we are talking about are not commercial yet, are still in scientific and technological development. So this may be
Exactly.
important to say.
We
But
have to make that division because many are technologically viable, but unless they're commercially or commercialized, they're not economically viable. Others are in place, and it's just a question of getting traction. One of the big things with renewable energy, with alternative energy, is getting scale, getting traction, uh, getting adopted by a wider segment of the world.
yeah, but it's important because it's not commercial yet. It's not being applied to some cases, and only in scientific and university research.
Not all of them, Cavagna. Some of these
Not all.
are. Yeah. So, and
Yeah,
I think this is the challenge because when many things start small, of course,
yeah, that's
and
right.
they're applied, for example, in Finland and in South Korea, and you say, well, South Korea is not really that significant, but
But it's
if a technology is applied commercially there, there's no reason why it can't be done in Taiwan, and then it can't be done
true.
in other countries. So it once things get going, they pick up speed. So this is an
Yeah.
exercise in forecasting, and as you know, forecasting the future is kind of tough.
Yeah, that's right. Let me only show that we have people following us today. Paula
Oh,
Kerber, good
okay.
evening. Good evening for you. Good afternoon for you.
Nice to have you, Paula.
Yeah. Yeah, please go ahead. You have some slides, I know, and I
Yeah,
will interrupt you frequently. You know that I can interrupt you. It's a
yeah.
pleasure.
I think this. I want to show this slide because it sets out basically a lot of the challenges, and there's others, and maybe some of these are mixed up. But renewables have suffered a lot in terms of image and even in terms of being implemented. And as you and I have discussed, they're something that maybe part of the world is promoting, and of course, is a big part of the world that's not on board yet. And there's reasons for that. But in general, there's problems, there's challenges. Intermittency, of course, the fact that many still need base power to supply the energy needs, or at least the electricity needs of their markets. Uh, when you have intermittency, you end up with storage needs so you can overcome those ups and downs. And in particular, in electrification, and we discussed this in the past, the existing electric grid all over the world, even China, which is the most advanced, of course, they're building almost from scratch. Electric grid in the world, very advanced, high voltage, direct current, leading edge applications. But all over the world, the existing electric grid is one of the major impediments to greater use of renewables. And in the U.S. as well as in Brazil and many other places that we know, there's a lot of instances where you have electricity being generated by renewable sources, solar, wind, and so on, which is doing no good. There's just no takeaway
Yeah.
connections to carry that electricity to markets that can use it. So you end up either with negative electricity prices, or you just don't connect. And that is, that's sad because after
And,
you've gone through all that.
it could be interesting to say that intermittency require normally dispatchable energy to
Exactly.
compensate this.
Exactly.
And the speed of grid investments on grid is not enough at this time to receive.
Everybody was enamored with renewable energy implementation, and they went gung ho with solar and wind, which of course garnered quite a lot of attention. And they forgot about the grid. And without in many countries, and you and I discussed this, the grid is basically over 100 years old and has been gradually being built. So the average age of this grid is decades and decades. And naturally, nothing lasts that long without failure and without needing upgrades, especially now when you need more than before a two-way road, because now you have dispatch from renewables and then you don't. So the grids have to go both ways. They have to control those excesses. You have management, grid management, and artificial intelligence can help, but there's just so much you can do. So there's many challenges, some of which we're being able to address, but that is a big challenge. So we also have the problem with many of these renewable energies still lack sufficient scale. Even when they're applied commercially, and many have been, you say, oh, that's fine, but is it going to substitute a nuclear power plant of over 1 giga, or is it going to or a hydroelectric dam that can be 10 times more? That's a scale that we might need. Of course, we discuss also many renewable energies still have in the back, problems such as critical minerals are still a limiting factor right now. Maybe, of course, we could grow production. We could, in fact, this is one of the things I bring out. We can start substituting some of the critical minerals with technology. That happens. And of course, there are technological limitations to some of these energies, which are also limitations. We need actually breakthroughs. It's not enough to say, oh, we're going to improve 10%, next year another 7%. That's not going to get us there. We
must be disruptions, yes.
A big step change so we can say, look, now we're on the road to being able to grow renewables to a significant portion of the world energy. And of course, we have performance limitations. This is, how far can we take the current renewable energy sources? And of course, some of them have still the problem of high capex, or maybe they're not so expensive up front, but they still have operating expenses that can grow in the back, especially with maintenance and so on. That is, for example, something we're beginning to discover with some of the older wind farms. So given that, I think that we can bring out right from scratch fossil fuels. Natural gas as LNG is one of the breakthroughs, and we discussed LNG a while back, and the prospects for LNG are tremendous. I am a firm believer that we are, exponentially growing the potential for LNG, and in fact, the U.S., Australia, Qatar, and many other countries are on a tremendous ramp up of LNG production, which will allow, for example, for intermittency to be supplied from gas generation. So the base power need or the intermittency can be, to a great extent, compensated with adequate electricity generating from gas generation. And if the country doesn't have gas, well, it can import LNG. Nowadays, that is a commodity. It's not something unusual. And the world is going in that direction.
Professor Cleveland, normally when we talk about renewable energy, we do not consider the costs of this dispatchable backup energy like LNG. Is it correct, or people are talking, including these costs in the total costs?
No, I think there's a reason why we shouldn't, because eventually when we have a sufficiently robust grid, maybe all of that might not be necessary. So if you say that a certain country has great generation from solar and wind, but it still needs to compensate intermittency or even seasonal with gas generation, and it doesn't have gas, it imports LNG. Well, if there were more robust grids, even regionally, not just within a country, so one country can connect with another one that might have hydroelectric or other generating sources which are not so intermittent, you could say that the intermittency could be compensated by the grid to a great extent. But
Yeah,
of
well,
course,
but
the grid has costs.
but the grid is only the receptor of the energy. The problem is the source of energy. So
Well, not really combined. There are regions, even for example, a continental country like Brazil has even today regions that are not connected to the grid, and they have, for example, the ability to generate electricity with diesel or renewable fuels, if it were the case, but they can't connect to the grid. If
no,
we did have 100% connected grid, there would be a great possibility of balancing out production of electricity from many sources. And then you might say that it doesn't matter if this reservoir is almost dry and you're not producing in this hydroelectric
can
dam
compensate with other sources.
because it can compensate. That on a sufficient scale is excellent. The problem is that the scale has to be big. There's no use having a grid just at a state level or something like that. It has to be almost at a continent level, certainly at a country level, but in smaller countries, it has to go beyond the country. So in that sense, the grid is almost one of the most important things. And nowadays, which I don't discuss here, for example, we're seeing data centers and so on recognize that because the grid is a limitation, if they build data centers next to power plants, or if they build power plants next to data centers, they get rid of that limitation. And that is a wonderful way of showing that, well, you don't have to consider, the costs of the grid if
These,
you build it right next door.
these are
Of
the
course,
case
they're
of
talking nuclear or something.
yeah, exactly. Microsoft and Google are applying
Yeah,
nuclear plants very close to their data
exactly.
centers.
A very logical step. I mean, this is thinking outside the box, very logical, but it's just recently that it really took off.
Yeah.
Yeah. If we go one step more, I think we discussed geothermal, very stable. It's renewable in the sense that the earth is generating heat all the time. So, especially with what I call the next generation geothermal, very high temperature areas that can generate geothermal, that is an unexplored potential, but it is, like we said before, it is a commercially exploited potential right now, not just the conventional geothermal, high temperature geothermal. So this provides base power and it's renewable. Obviously, it depends on geological favorability. So you can't do it right next to New York, for example, but there are regions in the world where this makes sense. And in this sense, it does have the capacity so that the scale is also there. There's many fields that you can probably scale up to giga power production, maybe from several wells, because maybe each well can go up to 50, maybe 100 megawatts. If you have 10, you have a gigawatt.
But geothermal, in terms of the total percent in the world, is very small, isn't it?
Very small. The point here is that it is very easy to scale up, because normally the difficulty in scaling is because you say, oh, the technology is not developed. But in this case, the technology is a technology that the oil and gas world has been using, the industry, for 100 years. So, maybe a slightly different place where you're going to drill and so on. But now there's no real challenge technologically to expand this. And if we get one project satisfactorily built, we have several now, there's no reason why you can't say, well, let's scale up 100 times, not just 2 and then 4 and then
and
8.
could be interesting, like nuclear plants that Microsoft and Google are applying to their data centers. Maybe good to this some data center that could be close to
Exactly.
geothermal plants.
This is in the gigascale also. So it's entirely possible that the next data center might be set up next to a geothermal source
Yeah.
like this. And these sources are all over the world. So when I say scale up, I don't just mean scaling up in the US or Canada. I mean scaling up anywhere in the world, because
Sure.
everywhere in the world we have high temperature
And that's
jobs.
good, because as a strategy to put data centers far from far from other, to be
Yeah.
let's say protected by wars and different things.
Yeah, that's a strategic consideration, of course. Now we recognize that. Um, and then if you're talking renewables, obviously we understand that you need storage, and storage for hydroelectric, for example. I saw an article the other day that said the only real storage at scale is pumped hydro storage in hydroelectric projects, because there you can pump a whole season when you have excess, and you can store terawatts hours of power. But there are lesser scale. We're not talking battery scale, because that's too small to be significant in the overall grid. But we're talking thermal storage, which 100 megawatt, 10 gigawatt hour capacity. We're talking hundreds of gigawatt hours capacity in hydrogen or methane storage underground. This makes viable a lot of the intermittent sources that are intermittent, not just on an hourly or daily basis, but maybe on a longer term intermittency, like wind might be the case. Maybe you could go a whole week without wind
Uh,
power.
could you please explain the thermal sand storage? You mean that the sand you put
You heat up the
energy?
sand. Yeah,
Mm.
you heat up the sand so much, up to 400 degrees centigrade, for example, that then once that sand is hot, it is storing energy in terms of heat. And when you need it, say when uh, renewable power isn't generating so much, you use that heat to generate electricity
And
through some
and
turbines.
how, and how long can you keep the temperature with the sand? 2 days, 3 days?
The temperature can be held a long time, maybe in terms of weeks even, especially if you go underground. Uh, but again, the limitation is not so much the temperature time that you can hold it, but the size. Because if you now talk about a tank, you actually have to build a tank, fill it with
Yeah.
a good thermal sand, and then you have a large tank. But maybe you can't have a tank with 1 million cubic meters, but you might have one with 100,000. That is a limitation, but it's
Yeah, it's a
now up
high
to a
cap.
big size.
Yeah.
Now, of course, underground storage of fuels, that is almost limitless, and we already have that to some extent, because we have the SPDR in oil, we have gas
Yeah.
storage in Texas, and we're more and more going to hydrogen storage if it's produced with renewable energy, and when there is no offtake, you can store it and then produce it again later. That can make hydrogen a little bit more viable. You and I know that personally, I don't feel very good about green hydrogen. It's still going to be very expensive. But if someone is going to go with that, of course, you have to make it more viable, even though it's more expensive and so on. So it's conceivably a very important, and we have seen that regardless of what I think, there's many green hydrogen projects going all over the world. And even in Brazil, there will be a lot of
Yeah.
green hydrogen projects going ahead.
Yeah.
I personally don't think that they make a lot of sense, but if they're going to go ahead anyway, because there's maybe a demand for green
But the
hydrogen,
point, this is
this
my
makes sense.
point. But in terms of scientific and technology development, it's good. The point is that if you apply to commercial side, so this viability is not so clear about hydrogen.
Well, this is what I'm saying. The viability is um, guaranteed by the fact that there are clients that are willing to purchase green hydrogen at green
With
hydrogen
subsidies, of
prices.
course.
Huh?
With
Oh,
subsidies.
regardless, as long as there's a demand, whether it's stimulated artificially, which I think is a waste of money, but if it's there, then it will get produced. And if it gets produced, it should be produced in a way that it can be shipped out regularly, stored, maybe shipped out by ship or pipeline or whatever. So this is a way of making something that is already almost uneconomical or is uneconomical other than subsidies, at least more viable given the technological limitations that it has in order to be stored and shipped. But I still consider green hydrogen a dubious proposition because, as
No.
you say, everybody is betting on it getting less expensive. I think that the least price that it can achieve is still going to be way above what is commercially viable.
Exactly. Exactly.
But, if we talk about batteries, there are batteries that are almost at grid scale because, even the Tesla batteries, you can't have, 500 acres of batteries. That's too expensive. But it is possible to have flow batteries that basically depend on tanks, giant tanks, just like oil tanks, for example, of electrolyte. And then the size of the battery is just the size of the tank. And you can literally have, 100,000 cubic meters or more of tanks because the battery itself is the middle part, is the part where the two liquids exchange ions through a membrane and generates electricity. And when you don't need that electricity and there's excess solar or wind or whatever, you just reverse the ion flow and you send out the charged electrolyte back to each tank. And if you have a big enough tank, you could conceivably have, obviously nothing is limitless, but you could conceivably have a grid scale battery storage. And nowadays, these are not that expensive because
And
it
how,
used to, yeah, it used
sorry,
to be
sorry.
limited by cost, which
Yeah, but
was
how
always,
big must be a battery to receive this energy from the intermittent energy from solar and wind? I mean,
well, say that you have a wind farm that's a 300 megawatt wind farm. You want a battery that can provide 300 megawatts. This battery can provide 300 megawatts if it has a big enough tank on each side. So
okay.
now we have solved that, and the question of cost was, and I would say isn't anymore a drawback. But now it used to use membranes that had expensive materials, vanadium and so on. Well, anytime you're talking about materials like that, you get into cost and critical materials availability and so on. But this is where technology is finding alternatives, basically carbon products that can provide the same membrane exchange
Do,
possibility as vanadium.
do we have in the world some of these batteries, batteries
Uh,
like this one?
Again, not commercially. We have
Okay.
operating flow batteries. I guess the scale is maybe in the thousands of liters, but this is already a large scale.
Yeah.
Any battery packs that the Tesla is touting, are very limited as well.
Mhm.
Australia has a large installation. It doesn't really make a lot of sense, but obviously Tesla got in there. But you have to use alternative battery concepts, and this is what will uh,
Okay.
first substitute those conventional batteries, lithium batteries. There's just no way that they can be cost competitive
Mhm.
with something like this.
Mhm.
And then um, we can go back to this hydrogen thing because you know that I am a great proponent of two types of hydrogen. gold hydrogen, which is maybe a little bit further off, even though we have more than one pilot project already in place, producing hydrogen at basically the same cost, $1 cubic meter of hydrogen that you can get with dirtier methods by injecting bugs in uh, depleted hydrocarbon reservoirs. This is fantastic because everything is there. No investment in great infrastructure. You need a truck there to just pump some of the bugs in, and it's been shown competitive. Um, in Brazil, we have an initiative going on at the university, federal university in Bahia, which is developing an alternative concept, just different microbiological routes, which is the only thing that differs. You're still going to use the same depleted oil wells and produce hydrogen the same way and ship it the same way, but now it's going to be inexpensive. Forget green hydrogen. The other hydrogen is the white hydrogen, the naturally occurring hydrogen. And geologists have, for the last 100 years, been looking for oil and gas, and they look for oil and gas in sedimentary rocks, which is where you would expect them. But they never thought of looking for oil and gas anywhere else because that wouldn't be very reasonable. But white hydrogen reservoirs are not in typical hydrocarbon reservoir rocks. They are in mafic, ultramafic, magmatic rocks, totally different, very hot, but fractured either naturally or artificially, and they produce hydrogen. So it's renewable in the sense that the hydrogen that you produce is going to be replenished down there. And this we have now found has tremendous potential. For example, in France, one of the largest natural hydrogen, white hydrogen deposits that has recently been discovered because no one ever bothered prospecting for white hydrogen in this kind of rock. And now that the world knows that white hydrogen can be a potential, the race is on all over the world for small startup companies to drill and prospect for hydrogen in different kinds of rocks and different kinds of geological environments than oil and gas. But the production technology is the same. Drilling has been developed by the oil and gas. Whether it drills those rocks or these rocks makes no difference.
Yeah, but hydrogen cause a kind of a doubt in terms of energy balance. People say that you use more energy to produce
Well, yeah,
hydrogen energy
green
than
green hydrogen, I agree, but natural hydrogen, no. It's there. It's just like methane. You take it, you burn it, you get energy. You take this white hydrogen, you burn it, you don't get any CO2, and you get energy. So it really is very cost effective, and the technology is there. And now we know that we've always had some natural hydrogen production, for example, in Africa and certain places where people accidentally discovered that and they said, oh, how interesting. Okay, this is fine. Small scale. Now we're talking reservoirs that can provide
yeah.
equivalent of 100,000 barrels a day of oil. Now you're talking a scale that can provide energy for cement plants, steel plants, that kind of thing, because this was the kind of industry that was very difficult to electrify because it's such high concentrated demand. But if you have concentrated, pure natural hydrogen without any CO2 emissions, it's a perfect marriage.
Mm-hmm.
And it's already being developed. I would say that the U.S. DOE is, of course, advancing this and pouring a lot of money into it, billions. But it's now the European Union has begun to wake up to this. First in France, of course, discoveries there, but we're going to find them elsewhere. But this is not the only area that we're seeing technological I would say more than evolution. It's almost a revolution. Now we're talking 26 million watt capacity, 26 megawatt capacity turbines for wind. If you're going to go to wind, which I believe in the long term is not the way to go, you know this. I've said that, well, 2030 maybe we'll still have a lot of wind. 2040 we'll say, gee, this was a dead end. But for now, and for the next 15 or so years, it's going to be a big deal. And you have to make it less expensive, further offshore, less impacts, and so on. And the Chinese seem to be leading the way. We're already talking about bigger than 26 megawatt. And the reason that this is important is because if you get very big, you get some economies of scale. You get less cost to set up these huge farms, especially offshore, which is where they would go, instead of doing double the number of turbines, which each has lots of difficulties and logistics for installation. You do less turbines, but bigger ones. And indeed, these are very likely to take up a large share of the wind energy generation in the world. Now, after 2030, 35, 40, I think all bets are off, and I think that we'll probably see that wind energy will not be able to continue to be competitive. If you have a wind farm built, of course, let it run until its life cycle is over. But lack of sufficient scale in wind, now we're getting there. And if we go beyond 26 megawatt, which seems very likely, we're going to get there. Now we're talking big scale. If you have 10 of these, you have a 260 megawatt installation. That is a huge installation.
Yeah.
And then, of course, solar is not falling behind either. Now we again have to say conventional solar energy generation, photoelectric, it was with silicon photoelectric systems. Now we're looking to leave behind silicon photoelectric generation because we know that has intrinsic limitations, something like 30, 33, maybe we can push it up a little bit more percent in efficiency. Silicon photoelectric systems will not be able to get beyond that. And they still have the problem of, even though silicon is abundant, you need very pure, expensive silicon. Yes, China is producing them cheaply, but there's a limitation to going cheaper than that. Mm-hmm. But multi-junction, these paint-on materials, they go beyond that, because now you're not talking silicon wafers. You're talking perovskite, calcium, titanium materials, which are maybe not super inexpensive, but they're way cheaper than silicon wafers. And you can basically paint them, and you can paint them over large surfaces. And now you're not limited to the same theoretical maximum that silicon wafers are limited to.
This is a good
deal. that is, and we already have this. Of course, maybe you can say, is it commercial? Yes, it's commercial because there's installations that are willing to pay higher prices to have a leading technology. But we are at the same dramatic cost reduction phase for multi-junction solar materials that we experienced in solar, in conventional solar. So these are likely to get much, much cheaper. Of course, China will be leading the charge again, but that's all right. If they supply these materials for the rest of the world, and the world can produce solar energy so inexpensively that it's just easy to paint everything with them, that's a gain also. And of course, very lightweight, less environmental impacts, all of these things. This, I think, gets to the performance breakthrough that we need. And the fact that it's already at a price point that it can compete is just a question of producing it at scale. And it's much easier to produce this at scale than it was to scale up production of silicon wafers. Of course, that was a fantastic achievement. Going from this scale up may not be so difficult because we're talking a completely different technology. You produce more, and all you do is paint it. Well, um, I think the last thing I wanted to talk about was the actual grid limitations that we touched on before. The U.S. just launched a new 2.2 billion program to upscale grid upgrades. It's tied to something like another 8 billion in investment. So, 10 billion doesn't sound so big nowadays in the energy industry, but this is only the first step. Once the U.S. DOE recognized that grid is the limitation, not
That's not a
anything else.
big number. It's not a big number, $10
No,
billion
it's
dollars.
not. But this is the first project that the U.S. DOE financed for grid scale, because they were always financing multi-billion dollars for wind and solar and hydrogen and all of these things, and they forgot about the grid. And now finally, I don't think it was me, but other people have been talking to them and telling them, hey, look, the grid is the problem, stupid, not the generating. So they woke up, and I think this is happening all over the world. The UK, which is a much smaller country, is putting 58 billion. Now we're talking much bigger numbers to integrate renewable energy resources. How? By building a more robust grid. This is where the grid has to go, because unless you upgrade the grid, forget electric cars, and you can't charge up cars with the amount of energy that's coming into most homes. So this is exactly where they have to go. Advanced conductors, grid hardening, and so on. In the UK, for over 100 years, overhead cables for electricity have been underground. They have been leaders in many ways. But now we need a whole new dimension. And you and I spoke a little bit about this. We spoke about grid. We spoke about grid technology. Everything from existing grids. You provide. Why is this? Sorry. You provide a means for the existing grid to be able to carry more electricity. They call it reconductoring. Building the same type of cable can conduct 3, 4, sometimes 10 times more energy. If you go into high temperature superconducting cable, you're now talking, many times more, and you can easily bury it in a very small footprint. If you talk about flywheel frequency control for the grid when there's fluctuations, now you can provide the grid with the kind of stability that you never could before. So we're seeing things that we weren't seeing before. Superconducting cable was a fantasy 10 years ago when I first started researching this. It was something that they were doing. Nowadays, there is superconducting cable in the US, in South Korea, like I mentioned, in Taiwan, and it's carrying electricity at capacities that you could not build overhead cable systems, because nowadays there's cities all over. You can't build these towers in those places. Everybody would say, no, I don't want these cables over my house. And this just gets around the problem. You dig a trench and you got it. So we touched on a whole bunch of technologies. There's a bunch more that I follow, but I'll let someone ask me, and maybe I can consult on that. But this is exciting news, and selectively you can say there are business opportunities in this. Yes.
Yeah, but I have a point for you, please. What's your vision in terms of investments on technologies, experimental technologies, objective technologies? How long, how big, how do you see this strategy for investments in technologies?
I don't even think that we need to put as much money into new technology as many people think. I think we need to put more into developing some of these technologies that we showed,
Just
because
existed.
scaling up and spreading out is the key. So once we have something that's demonstrated to be competitive, technologically functional, all you need is investment to put it into place in Canada, the US, France, Germany, Australia, Japan, and so on, Brazil, wherever. Uh, of course, research and development
As
should
always
always go
need
on. But, at this point, I think that the focus is on extensive
extensive.
development of the technologies we have.
Just
Even
exist.
some of these perovskite technologies. If we just invest in production, the growing the learning curve will
Yeah,
come.
but because you mentioned that we need some disruptive
Yes.
technologies, so that's the reason I'm asking you how
Well,
much money. Yeah,
this is how we perceive things, and I think for some of the existing generating systems like wind, we needed breakthroughs. For solar, we needed breakthroughs. Now we have them, so we have to develop them. For fuels, for renewable fuels, we needed a breakthrough. I think we have the breakthrough is looking for white
to
hydrogen,
replace naphtha in petrochemical plants, you need some kind of
including
breakthrough.
including this is the breakthrough that we needed.
Yeah, perfect.
Well, there's very positive news. Of course, there's a lot of work to be done, but hey, if it were easy, it would have been done 10 years ago.
Yeah, that's right. That's right.
Very
Great
exciting times.
conversation. Yeah, thank you. Thank you so much.
Thank
It was
you,
a great
Kabaya.
pleasure
Take care.
having
Bye
you
bye.
today. Yeah, bye.